going to be focusing on for the next two chapters, which we should finish the next two chapters. I doubt we'll get to 10, but we'll cover whatever on test 3 that we do get to. So chapter 8, we're looking at our periodic property of the elements, and we're relating what we learned in chapter 7 to understand bonding and to understand our trends. So our normal periodic table, right there, and if y'all are in the back, right over there, is designed to where we see repeating patterns of properties. We see a lot of repeating bonding properties. We've used the periodic table to say if it's in group 1, then it gives up 1 electron. If it's in group 2, it gives up 2 electrons. If it's a non-metal, it accepts electrons. We've looked at all of that. Now we're going to understand why that is by looking at and understanding the trends. So periodic law is just said that our elements are arranged in order of increasing atomic mass, and certain properties recur periodically, hence the name periodic table, because we see those properties recurring. We see everything in group 1. Notice that lithium to sodium is in order of increasing atomic mass. And then sodium has the same properties as lithium, but why doesn't fluorine have the same properties as lithium? Why are they so different? What's causing that? So that's what we're going to be really looking at. So we have elements with similar properties down the periodic table. And we can predict properties of undiscovered elements using this. Where the atomic mass didn't fit, he reordered them by different properties, so that's why you have those things like tellurium in random places, and we have those 2 separate columns on the bottom. So this is just showing how after he put the periodic table together, when he put this together, we didn't know all the elements that we know. But he was able to predict unknown elements. So these are his predictions, and these are the actual properties of the elements once he found them. So for example, he predicted that there would be an element of an atomic mass of 68 AMU, and there is. Now, of course, we know based on isotopes that it's actually a bit of an average, but 69.72. He predicted the melting point would be low, and the density would be 5.9, and it is actually the right density. And he predicted the formula that it would react with oxygen to form an oxide X2O3, and it does, Ga2O3. And it also, he predicted XCl, and it does come 1 to 3 with Cl. So he was able to predict that before it was ever found. And he also did that with germanium. So they do provide a prediction. It allows us to predict it, but it didn't explain the patterns. So it was great, we have it in these patterns, we're able to see it, but it's not explained. And personally, I'm going to tell you, you might not remember everything from this class, but if you understand the basics, then you can apply it and just do a small review and understand it. And this class is going to be applied to multiple chemistry classes. So if you're a science major and you're required to take this in 106 and organic chemistry, and if you're a chemistry major, further chemistries, even though you might not be always solving word problems, you're going to be using this basic information forever in chemistry. So if you understand it and you really get the basics for it and you're not just memorizing, you're going to have a tool that you can use for the rest of your life, other than just memorizing it and forgetting it right after the exam, which is, let's be honest, if we're memorizing, what we're typically doing. And most of chemistry does build up on these basic properties that we're going to be talking about in this chapter in chapter 9. That's basically all of chemistry. So we're really going to look at the why and understand the why and map it out. So we already talked a little bit about quantum mechanics, and quantum mechanics explains the periodic trends pretty well. So remember, we talked about those quantum numbers, N, L, ML, and MS. We're going to apply that to our periodic table trends. And again, we're not really going to solve the wave equation, but these quantum numbers solve the wave equation. Remember, no 2 electrons in an atom have the exact same 4 numbers. At least one number is going to be different of each electron in the atom. So we're going to look at mapping that out and understanding that. So first off, let's talk about MS, or our spin states. Now this was done experimentally. In 1925, Stern and Gerlich demonstrated that if you took a beam of silver atoms, then it's going to split into two streams if you put it in the presence of a magnetic field. So we termed that spin states. And basically what that said was we had some sort of spinning charged particles, and it created its own magnetic field, but half of the magnetic field interacted with the applied magnetic field, and half of them negatively interacted with the applied magnetic field. So what that suggests is half the atoms have a certain spin that's pointed what we typically show as north, and then the other half the atoms will have an equal spin but pointed in the exact opposite direction, which we usually represent with up and down or north and south, but that's really, really simplified. I just want you to understand that's really simplified. So if we had an external magnetic field, and let's say it was oriented up, then that would interact with the spin up states, but the spin down states would have a negative interaction with it, therefore splitting the beam. And that's what was seen experimentally. So that brings us to what we see. We have a fundamental property of all electrons in that they spin, and since they're charged, they create a magnetic field. All electrons have the same amount of spin. We don't need to quantify that number. We can. That number can be quantified, but it's not necessary for us to do right now. We don't need an exact number. All we need to know is that the electrons are either spin up or spin down. So we represent with our MS that quantum number as plus 1/2 or minus 1/2. And again, that 1/2 quantifies it, but it's not exact, the actual magnetic field it presents. But it gives us an idea, and it's a way that we can understand it. So typically, what we see is magnetic field produces an attractive force, the opposite magnetic fields. So you have allowing two electrons to be in one orbital, because even though they're both negatively charged and they can repel each other, because they're spinning in opposite directions, they attract each other and they cancel each other's overall magnetic spin out. Typically what we show, each electron is representing by a half arrow in an orbital, and here we're showing our orbital as a box, but later on we'll kind of evolve to just showing our orbital as a line. But either way, we're showing an orbital there, and an electron is either shown as spin up with a half arrow or spin down with a half arrow, where the half arrow is pointed down. So let's talk about how the electrons can go in the orbital. So because no two electrons can have the same set of 4 quantum numbers, and again, we'll show that with these representations, no orbital may have more than 2 electrons, and those 2 electrons must have opposite spin. So when we're filling our electrons in our orbitals, each orbital can have a total of 2 electrons, but one electron has to be spin up and the other electron has to be spin down. If we have 2 spin up electrons in the same box, they're going to repel each other, and that's really high in energy and unlikely to occur. So instead, we'll have spin up and spin down. If you know the number of orbitals in your subshell, you can figure out the amount of electrons in each sublevel. So remember our S subshell, our ML is 0. L is 0, so ML can only be 0. So that means we have 1 orbital in that S subshell. So it can have a total of 2 electrons, 1 spin up and 1 spin down. If we look at L equals 1, that's our P subshell, and we have 3 orbitals, our ML, -1, 0, and +1. So if it was completely filled, wow, this thing is not calibrated. If this orbital was completely filled, we'd have a total of 6 electrons. Then if we look at L equals 2, remember our ML is negative to positive, so that'll be -2, -1, 0, 1, and 2. we actually have 5 orbitals in that subshell, so we can have a total of 10 total electrons in that subshell if it was completely full. That's the maximum amount of electrons. It might not be completely full, but it can't have more than those 10 electrons. Let me see if I can fix this. That's better. So that's a total of 10. If we look at lastly our F subshell, then our L is equal to 3. So we have a total of 7 possible orbitals. -3, -2, -1, 0, +1, +2, and +3. So if we have 7 orbitals, that means we can have a total maximum of 14 electrons. So 2 electrons in each box. So that's what we see with this. And Pauli's exclusion principle states that we have to have 1 electron spin up, 1 spin down, and we can only have a total of 2 electrons in each orbital, which we represent by boxes. So let's look at helium. Helium, there it is on the periodic table. It is number 2. And it has a molar mass of 4. And it's one of our noble gases. So helium has 2 total electrons, and we know that because its atomic number is 2. So it has 2 protons, and when it's neutral, it has to have 2 electrons. Recall that from our first 2 chapters when we really broke that down. So we have 2 electrons, and we're going to be bringing a lot back from there. So you might have to review that for, say, answering these chapters. Because you should know if I give you an atom, how many electrons it has in the neutral atom, how many electrons it would have in a charged atom. You should be able to figure that out. You know that already. So both electrons are going to be in the first energy level because it's in the first level of the periodic table. So it only has a 1s orbital. Its n is equal to 1. So its L is only equal to 0. So both electrons are in the s orbital of the first energy level. And since they're in the same orbital, they have equal and opposite spins. So we can represent n is 1 because it's in the first row of the periodic table, and that's going to determine our n. Our L has to be 0 because L is n minus 1. Our ML must be 0 because we don't have any negative or positive of 0. So therefore, we can either have an MS of +1 or -1. So if we represent that as a box, we would show our 1s orbital, and it would be full with our MS of +1/2 and our MS of -1/2. And even though all the other quantum numbers are the same, we don't have the same 4 quantum numbers because these two are different, which is what we have to have for each electron. If they were both spin up, then they would both have the exact same 4 quantum numbers, and that's not allowed. So we're gonna start looking at electron configurations and figuring those out. So let's look at the electron configuration and how we would map that out. And that's really mapping out all of our electrons and what they're in. So first off, the ground state of an electron is the lowest energy orbital it can apply, because if an electron is in a higher energy orbital than it should be, then it would be what we call excited, and it would be less stable. So what we're going to be mapping out mostly in this particular class is going to be our ground state, our lowest energy electron orbitals our electrons can apply. When we show these, our electron configurations are typically written as this. What we see is this 1 that represents our N. So what we're looking at is hydrogen. Hydrogen has 1 electron. Its atomic number is 1. And because it has only 1, N is the highest it could be is 1, then we only have a 1s orbital. So the S clearly represents the s orbital. And then superscripted, we have a 1 here. That represents the number of electrons in that orbital. Remember, an S can only have 2. A P can have a total of 6. A D can have a total of 10, but it can have less. And an F can have a total of 14. So if you show an S, it shouldn't have 14. An S orbital, which only has an ML of 0, can only ever have 2 electrons in it. As our atoms get bigger, our electron configuration is going to get longer because we're going to have more orbitals and we're going to have more electrons. And each electron has to be in an orbital. So we're going to map out where all of the electrons are for our ground state of any given atom. So that's what we're representing with the electron configuration. And unlike when we're showing things like our formulas, we do represent that 1 at all times. So we are not ignoring ones like we do with charge, where we just put a plus instead of a +1 and everything like that. We do want to represent the 1. So this is our electron configuration for hydrogen. We only have a 1s orbital, and it's only half filled. We only have 1 electron in it. That means that our normal isotope of hydrogen does have a net magnetic spin, and we will actually get a magnetic reading if we have an applied magnetic field towards it, which we utilize in nuclear magnetic resonance spectroscopy, which is also, for the molecular level, in the whole body level, what we call an MRI, which are representing the fact that hydrogen has an odd number of electron spin states. So that's where an MRI machine really comes from and the basics of how it works. And when you take organic, you're really going to delve into how that works and look into the physics of it, actually. But we're not going to get into that in this class. So helium, which has 2 electrons, its electron configuration is 1s2. It looks very similar to hydrogen, but it has 2 electrons, so its electron configuration, its s orbital, is fully filled. So again, our number designates our quantum principal energy level. The letter is the sublevel, S, P, D, or F, and then the superscript designates the number of electrons in that specific sublevel. So we often represent an orbital as a square, and the electrons in that orbital as those half arrows. The direction of the arrow represents the spin of the electrons, either up or down is what we typically use. And again, that's just a pictorial representation of what's going on. It's a bit more complicated, but it explains enough. So we show it that way. So this would be an unoccupied orbital. It has 0 electrons. This would be an orbital with 1 electron. And this would be a filled orbital in this case. So when we look at helium, which is a 1s2, it would look like that last case. And we would typically show it like this. The fact that the box is blue is irrelevant. You can just draw it as a box. So here we're looking at an electron configuration. How many electrons are present in the 1p suborbital? So here's our 1p suborbital, and we have 6. So the answer is 6. How many electrons are in the 1s suborbital? 2. How many electrons are in the 2s suborbital? 1. Now here's the question. The 2s suborbital has a quantum number of 2. Do you think that's further away from the nucleus or closer to the nucleus? Further. So all of these, our 1s, our 1p, our 2s, They all have different energy levels, and as we increase away from the nucleus. So we're going to be pictorially understanding that as well, but typically these electron configurations are just written across, and we know the difference in energy. So we'll be looking at that as well. So the sublevels in each principal energy shell have hydrogen, all have the same energy, because hydrogen only has that 1s orbital. We call orbitals that have the same energy degenerate, and that's a term that you need to remember because you're going to hear it a lot. So if our subshells, all 3 p orbitals of our p subshell are going to have the same energy. So we call them degenerate orbitals. But our 1s subshell never has the same energy of our 2p subshell. So those are not degenerate. Those have 2 different energy levels. For multi-electron atoms, the energy of sublevels are split, causing electron repulsion. And this is just representing, now this isn't quite correct, because this is sort of looking like that these subshells have different energy levels, which isn't really, it's sort of the case, so let's delve this down. If this is my nucleus is here, I can have a 1s. And at that 1 energy level, I can only have an s. Because n is 1, so all I can have is an s orbital. As I go to the second energy level, I can have a 2s, and I can have a 2p. So that would represent 2 different energy levels. Then as I go up even higher, at the 3 principal energy level, I can have a 3s, a 3p, and I can even get to 3d. I can't ever have f in the 3 energy level because 3 minus n is never going to give me that 4 for f. So the closer we are to our nucleus, the lower in energy we are. So to understand our sublevel splitting, we're going to look at this in a little bit clearer. We're going to look at our interactions between our charged particles, which is Coulomb's law. Remember, negative charges repel, like charges attract. And remember, what charges our nucleus? Our nucleus. Our nucleus is mostly neutral, but our nucleus overall charge is positive. It has neutral neutrons, and it has positive protons. Our nucleus is positive. Our overall atom, if it's neutral, is neutral because it has an even number of electrons and protons. But our nucleus is positive. So our electrons that are closer to the nucleus are going to interact more with that positive charge, and that allows them to be lower in energy because they are starting to balance out. But as we get further away, then our electrons are going to be blocked from the nucleus by the electrons in the lower sublevel, and they're not going to feel that positive charge as well, so they become what we call less stable or higher in energy. So that's what our Coulomb's law is going to represent with numbers. The repulsion between the electrons in the cloud versus the attraction between the electrons and the positive nucleus. So we're going to be looking at that, and that explains a lot of bonding. We're going to look at that through 2 chapters, really. We're not just going to be looking at it in this chapter. That brings about shielding, meaning that one electron in a lower energy level can shield another electron from the full positive charge of the nucleus, which, remember, is what the electron wants. The electron wants to be balanced by the charge of the nucleus. So shielding is also going to affect our splitting and our sublevels, our difference in energy. So those 2 things are important. How much of the positive charge are our electrons getting, and what's that interaction? Plus, how much are other electrons blocking that positive charge? Also, this last thing that we're going to have to break down more than just a sentence is called penetration, how one atomic orbital can overlap spatially. And remember, we use a mathematical equation to predict the probability of the electron in the orbital, and we show it with shapes like a sphere and a dumbbell. So we can have some overlap spatially, where some of our electrons are penetrating into another electron closer to the nucleus. So we're going to have to look at that in more detail. That one's not so easy for me to explain in one sentence. So let's start with Coulomb's law, which is our attractions and repulsions between charged particles. And remember in the first week of class, I broke down charges and I said that positive like charges repel, opposite charges attract. So this is just a chemical or a mathematical equation to represent that. Our potential energy E, and it's not so much important that you memorize this equation, but understand what the equation is telling us. So the potential energy E of two charged particles depends on two main things. Their charges, if we're looking at, let's say, two electrons, electron 1 and electron 2. If we're trying to figure out our potential energy, then we need to look at the charges of electron 1 and electron 2. And then second, we need to look at how far away apart they are from each other in space. So we need to look at their charges, and we need to look at how far apart they are in space. If we're talking about an electron and a proton, then again we're looking at the charges of the electron and the proton and how far the electron is from the proton in space. And opposite charges are going to give us a lower energy, but like charges repel, so that gives us undesirable energy. So conclusions from Coulomb's law is two things. Coulomb's law showed that like charges repel each other. For like charges, the potential energy is positive, and it decreases as the particles get further apart. And remember, we're always trying to get our molecules and our atoms always want to exist in a level of the lowest potential energy possible. It's most stable state. So that's how we see that our like charges repel. Coulomb's law shows that as the like charges get further apart, our potential energy goes down because they're not interacting with each other as much, so they're not repelling each other as much. Coulomb's law also shows that opposite charges attract each other because the potential energy is negative and becomes more negative as they get closer. So as our potential energy becomes more negative, that means we have more stability, less of that unstable potential energy. So that's what our Coulomb's law shows us. And again, you don't need to, I don't think I have any examples where you're actually using this calculation. I just want you to understand that the potential energy both is dependent on the two charges and how they interact with each other and how far apart from each other they are. That's the two most important things from this equation. There's 4 pi E0. That's not something, that's a constant that just changes the number, but we are just looking at whether the potential energy is positive or negative. That's all we're looking at. The third thing is the magnitude of the interaction between charged particles increase as the charges of the particles increase. So electrons with a 1- charge is more strongly attracted to a nucleus with a 2+ charge because the 2+ charge is bigger. Now remember, one electron always has one negative charge, but our nucleus can have multiple electrons in the center. This is going to really explain why when we lose an electron and our atom becomes overall positive, it's typically smaller than our starting atom. And it has to do with this concept, that the more positive charge in the nucleus, the more it's going to pull electrons towards it. So that's what that's saying. So the bigger the charge, the more of that attraction you get. So those are the 3 things from that equation that I want you to understand. You don't really need to solve the equation, just want you to understand those 3 things. Now let's talk about shielding. So if we're just talking about hydrogen, we only have 1 electron, we only have 1 proton, it's great. It's a really simple system. The system gets a lot more complicated once we have multiple electrons. So for a multi-electron atom, any one electron experiences a positive charge from the nucleus. Now how much positive charge is dependent on where it is in the energy levels, what orbital it's in, and negative charge from other electrons, and we call that repulsion. So we have this electron-electron repulsion, and each atom has some balance between the electron-electron repulsion and the positive charge attraction from the nucleus. It must, otherwise no atoms would exist if we didn't have some balance between them. So when we're representing that wave function, we are in agreement with showing what would be the most likely, most stable atomic state of each atom based on this concept. So what's shielding? What shielding says is, if we have these two electrons and they're in the 1s orbital, and then we have this electron in the 2s orbital, that electron in the 2s orbital is not only further away from our nucleus, it has a 3+ charge, so we're assuming this is lithium, just based on this drawing, because lithium has an atomic number of 3. So that would be 3 protons. Remember, your atomic number is dependent on your number of protons. So, not only is it further away, but it's also being shielded from the positive charge by these electrons in the lower energy level. Because those electrons are giving repulsion and blocking some of the positive charge in the nucleus. And the nucleus is always in the middle. That's not moving. So the further the electrons are away from the nucleus, the more it receives that repulsion from the electrons that are more into it. And that's why we'll typically look at, when we're talking about bonding, interactions between our electrons in the outermost energy level. Whether they're given up, or electrons are accepted, or they're shared, we're always going to talk about electrons in the outermost energy level, because they're the ones that are not attracted to the nucleus the most. They're going to be the most shielded, they're going to be the furthest away. So the highest in energy. So that's what shielding is. We're getting those inner electrons, or shielding the positive charge from the outer electrons. So we're only experiencing about +1 of the charge, not the full 3+ charge. Whereas those 2 electrons that are closer to it are filling that whole 3+. So they're held closer to the nucleus. Now the last thing is this concept of penetration. So we have to look at this one in a little bit more detail. It's a little bit harder to understand. So if an electron is further from the energy level, but it comes close to the nucleus, the electron penetrates the electron cloud for the lower energy level and begins to experience more of the charge from the nucleus. As the outer electron penetrates into the region occupied by the inner electron, it just experiences a greater nuclear charge and a lower energy. So if an electron can penetrate into a lower level, it's going to feel more of the positive charge. So that's what we're looking at with the concept of penetration. And we're going to map that out in a bit more detail in a second. So we can graph this. And what we're seeing here is a 1s, a 2p, and a 2s orbital. And what we see is probability of it being near the nucleus. So that's what we're really looking at. And the splitting that we see pattern can result when the radial distribution of our function that the 2s orbital penetrates more deeply into the 1s orbital than the 2p. So what does that mean? That just means that the 2s is getting closer to the nucleus than the 2p is, even though they're in the same even though our principal energy level is the same. 2s and 2p are not at the same energy. 2s can penetrate closer to our 1s orbital, and it feels more of the positive charge, whereas the 2p is further out. That's all we're looking at with that and shielding. So the result is that the electrons in the 2s sublevel are lower in energy than the electrons in the 2p sublevel. So even though the quantum number is 2 for both 2s and 2p, they're not at the exact same energy level. Though they're still closer to each other, we call them in the second subshell. But they do have different energies. So what 2s and 2p are not is the jitter. Now all of the p orbitals in the 2p are going to be equal energy to each other. But the 2s and the 2p aren't. Then when we go to principal quantum number 3, and we have a 3s, a 3p, and 3d, 3s is at one energy, 3p is at another, and then our 3d is at a higher energy level because of the shielding and penetration. So let's map that out. If we have hydrogen, we only have a 1s. If we go something like lithium, lithium's in that second quantum energy level. So lithium has a 1s, but it also has a 2s and a 2p. And remember, p has 3 orbitals. So these orbitals are represented as circles in this graph. Then if you look at something like, let's say, sodium. Sodium's in that third principal quantum level. It has 11 electrons we have to be able to put in. So sodium has the 1s, the 2s, the 2p. But it has that third quantum energy level, so it has a 3s, a 3p, and a 3d. And 3s, 3p, and 3d are in the same sublevel, but 3s is lower in energy than 3p. 3p is lower in energy than 3d. Then if we look at something like potassium, potassium has that quantum energy level of 4. So potassium has all of this, plus it also has a 4s, a 4p, 4d, and 4f possible orbitals, because it has that quantum energy level of 4. And then if we look at that 5 quantum energy level, and 6, and so on as we're going down the periodic table. Yes?
Okay, so an element, for example, like you're saying, like it has like the 4s, but electrons, but it has that whole sublevel from S to F.
As we go up in quantum energy level, we have all of those orbitals, but they're all going to be more inner.
So like the electrons aren't located building the 4p, 4d, 4f.
They might not be. It depends, and we're going to look at filling this in a little bit. Just because the principal quantity level, like potassium, says it has the ability to have these 4p, 4d energy levels, it doesn't mean they're going to be full. It just means that they can have those energy levels. So we're going to look at filling them. Now notice potassium only has 19 electrons, but as we go over to arsenic, we have 33 electrons. It's also in that 4 quantum energy level. So it's going to have more filled orbitals. So it is dependent on the amount of electrons we have. But right now I'm just showing the possible orbitals. We're not filling them. And we're talking a little bit about our energy. There's a couple of things I want you to note with this. One is, because of penetration, the sublevels within an energy level where our quantum numbers are the same, 2, 3, 4, and so on, they're not degenerate. Also, I want you to notice that our 3p orbitals are always degenerate, our d orbitals are always degenerate, our f orbitals are degenerate with each other, but our 4s, 4p, 4d, 4f are never at the same energy level. They increase as we go up from s, p, d, and f. So they're not degenerate. Penetration of the 4th highest energy level, when you start getting to those bigger elements, is strong that sometimes the S sublevel can actually be lower than the F of the lower quantum energy level. We really don't see this too much until we get into really much larger quantum numbers. So for hydrogen and helium, we only have 1s, it's irrelevant. When we look at things in the second row, carbon, nitrogen, oxygen, we don't see this because we only have 1s, 2s, and 2p. But as we get higher, we start getting some of those 1s orbitals because of penetration getting lower into a lower quantum number suborbital. So this is really, really starting to get relevant at this 4 stage, where the 4s is actually kind of getting into the 3D sublevel. And then lastly, as you get further from the nucleus, the difference between the sublevels gets smaller. So for really small atoms, the sublevel difference is pretty big because the nucleus is still close enough to where it can still feel it. But as the electrons get further away, as we get more energy levels, the difference between the energies gets smaller because none of them's filling the nucleus as well. We have so many electrons shielding. So what we'll see reactivity-wise is that as we get bigger as we get bigger atoms, it's easier to excite to higher energy levels because the distance is shorter. So that's one thing that we do notice, is that as we get further away, this distance between the energy levels do get smaller. So for some of the elements, we get multiple electron configurations that work. That's usually for the bigger elements, things like in that 6 quantum level. So we'll look at some of those. So now we're going to talk about filling. Just because it has the possibility of having those orbitals doesn't mean those orbitals are going to be filled. It depends on the amount of electrons you have. So energy shells always fill from the lowest energy to the highest, because the ground state electron configuration has all electrons in the lowest possible energy levels that it can be. So we always fill closer to the nucleus, 1s first, then 2p, and so on. So we always fill as we increase in energy. Sublevels fill from lowest to energy to highest, and we call that Aufbau principle. We're always filling from lowest to highest. Now the next thing is, orbitals that are in the same sublevel have the same energy. So all p's, they're degenerate. So no more than 2 electrons per orbital. So per box, we can only have 2 electrons. We already talked about that. And the last thing, we have to follow Hund's rule when we're filling, otherwise we might get a wrong designation of how the electrons exist in the orbital. So Hund's rule states that if you're filling degenerate orbitals, you always fill unpaired before you come around in pairs. And the reason for that is, if you don't, then in some cases you might get the wrong electron configuration, which doesn't describe what we see in nature. And remember, this is describing what we see in nature. That's what we're trying to do. So if you fill it wrong, you're just filling something that's not going to explain reactivity. So that's why we're following this rule. So let's say we're filling the P's. So let's say we're doing this one. We're going to fill our 1s first. We're going to fill up down with our little half arrows. Bless you.
Bless you.
Then 2s is next highest in energy. So we'll fill those two. Now when we get to 2p, those 3p orbitals are degenerate. So we're going to fill them first unfilled, and then we're going to pair them. And in this case, we were showing 1, 2, 3, 4, 5, 6, 8, 9 electrons. So for 9 electrons, this is the correct way to fill it. If you don't follow Hund's rule, you won't get the same pattern. So you need to make sure that you're following Hund's rule when you are filling it. Sometimes it won't make a difference, but oftentimes it will. So we need to make sure that we're following it. This is the way that it's often shown straight across. And I don't really like that so much. I much rather actually representing the energies. So what we typically draw once we get to organic chemistry is we actually draw them the way they are based on energy. So when you're filling them, let's say we're filling nitrogen. Nitrogen has a total of 5, well, let's do oxygen because it's fine. Oxygen has a total of 6 electrons. I already filled these 4. If I don't follow Hund's rule, then I would do this, and that's not actually how oxygen bonds. The correct way to show and represent the bonding for oxygen is this way. So that's why we want to follow Hund's rule. We don't want to pair until we've put a half electron in each of the degenerate orbitals. So this just represents the energy. We always draw our energy going up, but you'll often see in the book it going across, and the degenerate ones are kept closer together, representing that they're the same energy. And for these iClicker questions, it probably would really help if you had a periodic table in front of you. I mean, we have them. There we go. We do have them, but it's a little bit easier to work with one right in front of you. So I suggest bringing in a periodic table. Now for a quiz and everything, I'll give you one. But for while I'm lecturing, it'll be really useful for these next 2 chapters to have.
Are we going to go over the orbitals at all?
Yes.
Yes.
I didn't tell it to go forward. I don't know why I did. Okay, so first, I'm going to show you how to do the electron configuration in the way that I don't like. And then we're going to get to actually using the periodic table to do it, which makes much more sense. But I'm first going to show you the way I'm not really a big fan of doing it. Now, first off, the electron configuration is representing our ground state. So you can always draw this and fill in, and then write this electron configuration. So if I have this would just be for my electron configuration. 1s, I have 2. 2s, I have 2. And 2p, I have 2. And that would be my electron configuration. So you could draw that first. You don't have to, but you could. And using the periodic table I do think is easier, but we'll get to that in the next class. So if we look at krypton, we have 36 electrons. The electron configuration is all of this. Pretty much for most of our ones, until we get to our higher energy level, everything's going to be full. Now, here's the thing, for a noble gas, all orbitals are always full because that's what makes a noble gas so unreactive. The fact that all the orbitals are full. So we'll see that commonly with noble gases. And that's why we see bonding, because every atom wants to be like the noble gas. So krypton has 36 electrons. So when it's neutral, if it has 36 electrons, these numbers should equal to the number of electrons that we have. So that's a key, because we're showing where all of the electrons are in the electron configuration. The other thing I want you to note is our electron configuration does show when we have penetration. Notice this is 3s, 3d, 4p. So when we get to those higher, those bigger atoms, notice that the 3d is lower in energy than the 4p. And we represent that with our configuration. Now, like I said, I'm going to show you the way to do this that I don't like as much. And then in the next class, we're going to look at using the periodic table to show this. And it'll make a lot more sense, I think. So a shorthand way of writing a big electron configuration is to just write the noble gas in brackets and then everything past the noble gas. Because that's really going to be the only difference between, let's say, potassium and calcium. The inner electrons are always going to look like argon, which is the noble gas before potassium and calcium. The difference between potassium and calcium are going to be in that outer orbital. So in that 4 orbital. So oftentimes, instead of writing the whole thing, you'll see it written as a symbol of the noble gas. So for example, rubidium, it's over there, it's 37. Notice that this and this is exactly the same because krypton is a noble gas right before rubidium. And the difference comes in the 5s subshell. So that's why often you'll see krypton in brackets, because that's the noble gas directly before, so the noble gas with the lower quantum energy level. And then everything else is mapped out after. And then you'll see, again, if we look at strontium, which is 38, it'll look exactly the same, but its 5s will have 2 instead of 1 electron. So that's why we can do that. So you'll sometimes see that. I don't know why it's doing that. I'm going to skip this slide, and I'm going to get back to it in a second. So what I want to do is go through one example before we go today. So ordering of the subshell filling in the ground state configurations. Start by drawing this. And again, I don't like this. I'd much rather the periodic table, but this is how the book goes through, so that's what we're going to teach first. Start by drawing a diagram where each energy shell on one row and list the subshells. So 1s, we only have 1s. 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, and so on. And bring the s's all in one row, g's all in one row, the d's and the f's all in one row. Now, if I'm looking at sodium, I don't need to go past 3d because sodium doesn't go past 3. But this is just in general. Then, draw arrows down through diagonals, looping back. So we'll first fill in the 1s, and then the 2s, and then the 2p, then the 3s, then the 3p, then the 4s, and that's how you're getting those quantum penetrations. So if you follow this, then you can fill the molecular orbital diagram. Now again, I don't like this route. I much rather use the periodic table, which we're going to talk about in the next class, but I wanted to introduce this so you can start doing your practicing. The periodic table actually explains why this is. So this is kind of just memorizing a route, which I don't like as much. So if we're looking at these, I want you to fill in those electron configurations and start practicing with these routes. And we're going to go into more detail in the next class, and then use the periodic table to do this, which I think is easier anyway. You guys have a great day. And again, make sure you're picking up your tests and quizzes before the break so you can really look over them.